I'm very happy to introduce Michael Lambert, who will tell us about double categories of relations. Please take it away.
Great. Thank you for the introduction. Thanks everybody for coming, sticking around. Thanks also to Bryce and to Tim for putting together this wonderful workshop. I unfortunately have only managed to be able to make it to a handful of talks, but it's been great so far. I hope to catch up on the ones that I've missed when they're eventually posted online. So what I want to talk about today is just kind of an overview of some work I did trying to answer a question that I will describe. Basically, trying to figure out which double categories are of the form relations on some regular category. Let me just start with some introductory commentary and preliminaries on notation. My apologies if I'm sort of laboring certain things or treading over ground that has been well rehearsed, but as I said, I've only been to a handful of talks so far, so I'm not entirely sure what I need to say and what I don't, but I'll just be brief here. The decorated arrows I tend to refer to as pro arrows. This is sort of recalling the idea of like a pro arrow equipment. Cells I tend to display horizontally in the sense that the pro arrows are horizontal as opposed to vertically. External composition of pro arrows and cells, I use a tensor for that. And the external identity, I use Y. I refer to the objects or the ordinary arrows that come with pro arrows and cells as the source and the target for the external structure, whereas the pro arrow, whereas a cell, right, has an internal pro arrow domain and an internal pro arrow codomain. I write external composition in diagrammatic order. And in order to distinguish all the tensors that will show up in various notations, I'm using a box for external monoidal tensors on bicategories. So I'm not going to give you a very extensive talk plan. Basically, this is an overview of some work that was recently published in TAC. The question just is maybe a relatively simple one. I mean, outwardly or ostensibly, it seems sort of simple. Which double categories are of the form rel, E on some regular category? So what are relations? They're just monomorphisms. So if you have a regular category, you can get a nice calculus of relations in a variety of ways. If you're willing to sort of mod out by an equivalence relation, you might actually get just an ordinary category of relations. Or if you didn't necessarily want to do that, you might end up with bicategory instead. And then finally, there is, of course, the double category of relations, where the ordinary arrows are just arrows in the category, and then the pro arrows are relations. And of course, you have this external composition, which is associative up to coherent isomorphism. And so there are a variety of ways of sort of axiomatizing in an elementary way, at least the bicategorical version of relations on a regular category. And one in particular that I want to focus on is the bicategorical axiomatization due to Carboni and Walters. They start off with this notion of a Cartesian bicategory, which is a bicategory equipped with a tensor, pseudo-functor, and an identity object. And under this tensor, we're asking that every object has the structure of a commutative comonoid. Every morphism is a lax comonoid homomorphism. The structure maps have right adjoints in the bicategory. And there's a certain uniqueness condition as well, which I won't labor. Based on this notion of a Cartesian bicategory, they then make definition that a bicategory relations is a Cartesian bicategory, where every object is what they call discrete, which is basically this Frobenius condition that I'll explain a bit later. But their big result is that every functionally complete bicategory relations is equivalent to one of the form rel, well, I said C here, on some regular category C. So I'll review this theorem in a bit more, well, not in more detail, but a bit more precisely. What we really have to sort of explain is what functionally complete means. But this was kind of my inspiration, and you know, we can see that Carboni and Walters did this, right? They had this nice definition of a Cartesian bicategory, of a bicategory of relations, and then they said, well, bicategories of relations with this extra property being functionally complete are precisely relations on a regular category. So I want to try to do the same thing for the Hubble categories, but only for certain kinds of double categories, because we need something to work with, right? So it seems to me that basically something that, I mean, I'm not going to say like every double category is an equipment, but I really like equipment, so I tend to sort of assume that if I just sort of have a generic double category as an equipment. This has been, I think, reviewed at least once, but essentially, right, being an equipment is a Hubble category where every ordinary arrow has both a companion and a conjoint, right? These are special pro arrows, which I know by F bang and F upper star. These come with some special base change cells and satisfy some equations. And this is pretty powerful, right? It turns out that to be an equipment, right, it's basically the same thing as that the source target projection is a bifibration. And the Cartesian and op-Cartesian arrows actually come about in a really special way. They come about as so-called restrictions and extensions of these little niches and co-niches, where you're essentially composing these base change cells in a specific manner. I won't really go into exactly how to construct those, but at least in the example of relations, restriction is kind of behaving like pullback, and extension is behaving like an image. Now, Eva Alfieri, in her thesis, gave a double categorical version of the definition of Cartesian for double categories. And my understanding was that this was to build on the Carboni and Walters definition. Her definition was a bit different. So if we work in the two category of double categories, pseudo-functors, vertical transformations, we get a diagonal functor, which I call delta, and a unique functor into the terminal, which I left unnamed. This double category is Cartesian if both of those have right adjoints. this has a lot of nice consequences. If you work with a Cartesian equipment, it turns out that each sort of Hom category between objects, let's say A and B, which is the Hom category of the pro arrows, right, as objects, it turns out that these actually have products. So I denote these products with a wedge and refer to them as local products, for reasons that I hope will eventually become clear, but I'm kind of working on the full justification of that. Although I think this is pretty common. This is the notation they use in allegories. I think they use it in the bicategories paper, and Eva used it in her paper as well, I believe. So basically, these are kind of some conditions that I just want to sort of ambiently assume. So in some sense, our question really is which Cartesian equipments are of the form rel E for some regular category E. Here's some examples of restrictions and extensions. So this one here, this cell rho, the niche is F and F on each side, and the identity as the codomain. And then this tensor of companion with conjoint, right, presents the domain of the restriction, and the cell is called rho. And I refer to these as the kernel of such a morphism. Likewise, if you instead extend the external identity on A in this sort of co-niche structure with F as the sides, and get this tensor of the conjoint with the companion, that's the co-kernel of F. So rho is a Cartesian cell with respect to the source target fibration, and Xi is off Cartesian. So if you're working in an equipment, we'll say that a morphism E is a cover if its co-kernel is trivial, and it's an inclusion if its kernel is trivial. We'll need these later. Okay. So now that we've kind of tried to set the stage a bit and actually refine the question, let's actually just look at relations a bit more closely. Well, first of all, rel itself is a Cartesian equipment, so that's good. It's also unit pure. So I encountered this in Eva's thesis again for the first time. I'm not sure I remember exactly if that's where it first appeared. So don't quote me on that as being the origin of this notion, but it's just asking that the external unit map is fully faithful. Rel has tabulators, and my apologies, I don't know if those have been defined carefully thus far, so I will make sure to review that actually, I guess it will be momentarily, probably in a few minutes. So-called tabulations are basic in the characterization of bicategories of relations. And actually being functionally complete is just sort of stacking more conditions on these tabulators. So what I really want to do is to say, okay, we're going to be working with Cartesian equipments. We're going to assume that they have tabulators. What else do we need to ask for with these tabulators to ensure that this Cartesian equipment is of the form rel E? So let's talk a little bit more than about the specifics with bicategories of relations. I threatened that I would be a little bit more precise about this, and so here it is. Specifically, it's a locally post-subtle Cartesian bicategory. And we have this discreteness axiom, right? So that every object in the bicategory satisfies this further property that the co-multiplication map associated with the comonoid structure satisfies this Frobenius identity. Some folks are very handy with like wiring diagrams and things like that. I can like convince myself occasionally that I really can disentangle them. I forgot to try to do that before this talk. I'm also not like entirely sure I've ever really convinced myself exactly what they really sort of mean. But as I was rereading Carboni and Walter's paper, I was interested more in the word that they chose, discrete. And the reason that they chose this word is actually proved in the paper in a remark. It's not exactly in passing, but it's definitely there. So Joyal and Tierney wrote this paper, right, on extending Galois theory of Grothendieck, and they have this notion of a discrete space. And it turns out that in this bicategory of semilattices that they work with, the discrete objects in Carboni and Walter's sense are precisely the discrete objects in this bicategory of semilattices. So what exactly does functionally complete mean? Well, again, I'm going to just hedge a little bit here, but the sort of like overview of it is that whenever you have a morphism from an object X into the identity for the tensor, the tabulation is another special arrow from a new distinguished object. And it satisfies some equations. Now, of functionally complete bicategory relations, it turns out that there's a special category that you can build from morphisms in the bicategory. It's the category of maps, which are those morphisms having right adjoints in the bicategory structure. You can prove that that category of maps is regular, and then B is precisely relations on that regular category. Okay, so this kind of tells us more like what we have to do, right? Like we're starting with a Cartesian equipment. We'll probably say it's locally Posettal. We'll say it has tabulators, and then we have to somehow find some sort of regular category that's built into the structure somehow, and then we'll actually show that it's equivalent to relations on that category. So in order to do that, there is sort of a missing starting point, actually. How Carboni and Walters have sort of structured this, right, is that first you need some notion of a bicategory relations, and then you do functionally complete. So we have a Cartesian double category, we have a Cartesian equipment, but what's the double category relations part, right? What's that sort of intermediate step before you tack on functionally complete? So let's take a look. It turns out that there is actually a key observation here that, to my knowledge, had not been made. And it's just that the horizontal bicategory of a locally Posettal Cartesian equipment is actually a Cartesian bicategory. This is in the paper. It's, it's a little fiddly, but not impossibly hard. But the point is that this just motivates a definition, right? That a locally Posettal Cartesian equipment is a double category of relations if this discreteness axiom holds in the horizontal bicategory of the Cartesian equipment. Now, I have to make some comments on this notation because, right, we don't want to get messed up with the tensors and the upper stars and everything else, right? What are these deltas? The deltas are the companion conjoint of the diagonal map that comes with a given object. Let's just say X. I haven't written in the X's here just to kind of control the notation, but So just straight delta is the companion of the diagonal map, ordinary morphism on an object X, and delta upper star is the conjoint of that map. The ordinary times, right, is the Cartesian structure for the double category, and the O times is the external composition. So it's the Carboni-Walters axiom, just with all the notation changed in the right way, so that we're actually working in the double category. Okay. So our question is, which of these are of the form rel E? Well, let's start with spans. It turns out spans were completely characterized. This is really neat. This starts with a theorem about the existence of Oplax-Lax adjunctions. If you have a double category, right, whose underlying one category has pullbacks, then you can actually say precisely when you get an Oplax-Lax adjunction to spans on the underlying category. This is when you have an equipment with tabulators. Roughly speaking, the Oplax functor takes a span and returns the co-kernel, and on the other hand, the lax functor G will take the legs of the tabulator of any given pro arrow. So the characterization of spans builds on this, adding some extra completeness conditions to ensure that the Oplax-Lax adjunction is actually a strong adjoint equivalence of double categories. So, in other words, D itself is equivalent to span on a finitely complete category, if and only if you have a unit pure Cartesian equipment that admits these things called Eilenberg-Moore objects. That's really the one that I'm interested in. The third condition is also very interesting, but really it's two, right? That we have a Cartesian equipment and it's also unit pure, and it has this extra completeness condition, the existence of these so-called Eilenberg-Moore objects. So basically, this is my plan of attack, though. Start off by assuming D0 is regular, ask when do we get an Oplax-Lax adjunction, and then what further completeness conditions do we need? And can we phrase them in terms of tabulators and get that Oplax-Lax adjunction is a strong adjoint equivalence? And it turns out that's exactly what you can do. So let's move toward that, right? We want to work with tabulators. So what are they? Well, I think the cleanest definition is just that a double category, right, has all tabulators if the external identity has a right adjoint. That's the really just like slick, beautiful definition. In particular, though, you might just want to talk about the tabulator of a pro arrow. Well, it's a special like apex object with a cell, right, from the identity on the apex object, satisfying universal properties coming along with the adjunction. So tabulators in REL are really nice. I mean, in fact, like it's basically just the relation itself. So the legs of the tabulator, they're jointly monic. And then they also have this strength condition that the pro arrow extension, right, the co-kernel is the original is the original pro arrow that you're tabulating. Pro functors also have tabulators, but very different kind of thing. They're still strong. However, they're definitely not monic, right? So in profunctors, basically the tabulator is going to be given to you by a category of elements construction. And so those guys are going to end up being some kind of fibration-y thing instead of a monic. I'm running on time here. Okay, good. So we said that functionally complete means that in a bicategory relations, right, means that arrows to the identity for the tensor have tabulations. It turns out, right, that from this assumption, in fact, every arrow in the functionally complete bicategory of relations has a tabulation. And these satisfy very familiar, well, now familiar looking properties. They're both strong and monic in a certain sense. Personally, I like how allegories phrase this. I mentioned allegories, I think, at the start. In case I didn't, allegories are another way of, you know, sort of elementarily axiomatizing the relations calculus. And they're very close to bicategories of relations. In fact, under certain conditions, bicategories of relations and allegories are essentially the same thing. And likewise, allegories have this notion of when you have a tabulation for an arrow, and again, these two conditions come up, that there's some kind of a co-kernel-y thing equaling the original relation, a strength condition. And then this is how they phrase the monic condition, which is a local intersection of sorry, not co-kernels, pardon me, which is a local intersection of kernels. They ask that the kernels intersected locally, well, of each of the legs, right? You intersect them, you get the identity. That's how they phrase monic. So this, I think, is the key for Cartesian equipments. We have local intersections. So we'll just jump right to the chase here. We'll skip, you know, just having certain tabulators or whatever. We'll just ask for all tabulators, and we'll ask that they're both strong and monic in these senses. L and R, right, are the left and right legs of the tabulator. The first one says that the arrow that you're tabulating, right, is the co-kernel of its tabulator. And then the other one is saying that the intersection of the kernels of the legs is trivial. Oh, okay, yeah. So, yeah, this is pretty good. And actually, I mean, I've actually sort of wondered whether this is really the right definition of functionally complete. I mean, it's kind of the allegory definition, but I don't know if it's quite enough, actually. And I'll explain why. Really, all you really need is monic, and this gives you the existence of this Oplax-Laxic junction. So we're going to start with a regular category, D0, underlying our double category. And the theorem is that the identity on D0 extends to a normalized Oplax-Laxic junction with relations on the underlying category if and only if three condition hold. It's got to be unit pure equipment, monic tabulators, and finally this kind of weird condition that the unit external unit cell associated to each cover in the regular category is an extension cell. So this is sort of a starting point. And what I want to do is try to explain and explain away in some sense, or summarize or synthesize all these kind of weird looking conditions. So to that end, let's just, well, what I did in the paper is I actually just like studied these functors, well, op lax and lax functors, and tried to really figure out like exactly when are these things actually pseudo, for example. And G is pseudo. Ordinarily, it's just lax. If there's this very strange condition, I'm calling it relations tabulate. And basically, right, this is just saying that if you have a relation, right, just an ordinary relation, a jointly monic, right, arrow in D, you ask that that's the tabulator of its co-kernel. This implies a lot, actually. It precisely implies that G is pseudo, and it also implies unit pure. So if we were to assume relations tabulate, we would already be making a pretty big improvement on this op lax lax adjunction characterization. It actually turns out it's a really strong assumption, and I'll explain that a little bit more in due course. It's certainly true relations. I mean, insofar as an, you know, the co-kernel is an extension, right? Is essentially an image. So here's the improvement. I do have a standing hypothesis here that D0 is regular. We actually get an adjoint equivalence from the identity, right? If and only if D is functionally complete, and then relations tabulate, and then this YE is an extension cell for each cover. So there definitely is a lot under the hood here that I'm not going to talk about. One point you might wonder here is like, well, why did you jump right from, you know, monic all the way to functionally complete? Well, the strength assumption in functionally complete is going to imply a Beck-Chevalier condition, which then in turn implies that the normally op lax functor F is actually pseudo. So that's why that extra bit is appearing there. But let's see if we can, you know, let's see if we can do better. So what I want to try to do is wrap up the first two conditions, namely the functionally complete and relations tabulate into one condition. And this looks a little weird at first, but what I want to do is try to justify it. So I'm kind of thinking of or referring to this as the existence of a sub-object comprehension scheme. So functionally complete says, well, if you have a pro arrow and you take its tabulator, at least you get a jointly monic arrow, which will define a sub-object. Here's a funny thing. This morphism, under the assumption of functional completeness, is an equivalence if and only if relations tabulate. So what I want to do actually is say that, well, I guess you can make the definition right for a functionally complete Cartesian equipment and say that the double that thing has a sub-object comprehension scheme if this induced map is a strong equivalence of categories. But I guess, you know, in order to make the definition, all you really need is a double category with monic tabulators, basically. Now, okay, so I've thought a lot about how to explain what's going on here, and I don't really know how I want to approach it right now. But let's see, what do I say on the next slide? Well, let's look at the consequences first. If you have such a thing, you get functional completeness, right? That's part of the definition. You get relations tabulate, that's part of the definition. You also get unit pure. So that's great. That wraps up a whole bunch of conditions. But this is really what I've spent some time trying to think about, right? Why is this a reasonable assumption? It looks like it's pretty strong and a little weird. I'm thinking of this as sort of a version of having a subobject classifier. I think that's what's really going on here. So if you go back and look at this map, right, you're taking a pro arrow and you get a subobject, and on the other hand, if you have a subobject, you would be able to come back and get a pro arrow. So I'm thinking of the pro arrow part as like truth object valued representations, right? Like morphisms into omega, or if you really wanted to take one of Lambiert's ideas very seriously, right? Set is a truth value object for the theory of categories. So a pro-functor is like a truth object valued representation. Now, if you worked with that example specifically, you wouldn't end up with subobjects necessarily if you were to comprehension those things, but you'd end up with something different. You'd end up with like a discrete op vibration. Now, you can sort of regard those as subobjects, though, right? Because they're part of the comprehensive factorization on cat. So I don't think the analogy is too crazy. But the crucial point here, right, is that when you have a subobject classifier, it's at least in a topos, right? Like it's a genuine bijection. You can freely just actually move back and forth, right? Now, I want to point out here that you might think, well, okay, I know about two toposes and stuff, right? So like, those have a subobject classifier. The representations, right, are supposed to sort of behave like pro-functors, and we only ask that this sort of representing structure induces a fully faithful functor. We don't ask for an actual equivalence. But I would point out, right, that if you stay inside small categories, you do have a genuine pseudo inverse for the elements construction. The reason admissibility comes in is because you insist on the representing object being part of the structure, right? You look at cat as a two topos by enlarging it, right? Enlarging the universe by sticking set in there and saying, well, no, actually we need a, something slightly bigger. We're not going to work with just, set small categories. And so it actually introduces this whole problem of admissibility, which could be avoided if you just didn't insist on the existence of the representing object. And the point is, by sticking with double categories and with pro arrows, you can hide the representing object. You don't actually need it. You just work with the pro arrows. This is another way of saying that size issues are really subtle. And my apologies to Rold and Street and Walters, who spent a lot of time actually wrestling with like Oneta structures and admissibility and all this stuff. Like, I'm just going to ignore it, basically. This is, I mean, it has some justification, I think, but it's also partly a contrivance in that I'm also, a little bit lazy. But I would say as well, right, that a lot, I mean, and this is something that I'm going to say without actually being able to completely justify it with a particular example that I have in mind, but it does seem to me that a lot of the power of at least a subobject classifier with ordinary toposes is that you really do get a genuine bijection. So I kind of want to see how that plays out with higher categories. but not just like infinity toposes and stuff, but like actually like, you know, non-trivially two-dimensional, you know, structures like double categories, for example. So in any case, here's the result. We can kind of start to put everything together now. We'll start with D0 regular. The identity functor is an adjoint equivalence, a strong adjoint equivalence. If and only if you got a subobject comprehension scheme in this other sort of nagging property, right, that every identity cell is an extension for each cover E. And that's the next condition that we'd really like to eliminate if possible. So let's try to do two things at once, right? When is D0 regular, and can we eliminate this last condition? Well, you might say, hey, this is a talk about double categories of relations, right? Where are they? Well, that's right here. If you have a double category of relations with a subobject comprehension scheme, you can prove that D0 is regular. So that's really cool. And this is where the discreteness axiom comes in. You might remember from Carboni and Walter's paper that the Frobenius identity actually implies modularity law for allegories, which is pretty cool. And that's exactly what you need to prove that covers are stable under pullback. Yeah, that's what I just said. Okay, great. And then the other thing is that you want to show actually that the covers in the equipment structure coincide or are essentially the same thing as the covers in the regular category. And that's the other thing you can get from assuming that you have a double category of relations. So actually, that just kind of wraps everything up. Turns out that if you have a double category of relations with a subobject comprehension scheme, that identity functor extends to a strong adjoint equivalence of double categories. So this is one answer to the question. There's still, I guess, is some sort of nagging question in my mind as to whether, you know, I should just be changing the definition of functionally complete to kind of honor the literature, or whether I really want to stick with this idea of having a subobject comprehension scheme to sort of like really emphasize this like subobject classifier like business. I kind of like the latter because I do think that there's some notion of double topos sort of lurking here, and I make some hints in that direction in the paper. Clearly, it's not going to be for subobjects necessarily, but the point is that both subobjects and discrete op vibrations are algebras for like a nice monad. And so there might be some way of saying, well, hey, you've got this structure with a monad, and we're sort of asking, right, that all of the pro arrows, you know, are essentially the same thing as certain algebras for that monad. So this is all very theoretical, though. One of the questions you might ask at this point is, well, why? You know, why are we doing all this? This started out as an exercise for me. I just wanted to learn by categories of relations stuff. Actually, incidentally, somebody asked me if I knew what a Cartesian virtual double category was, and I was just like, I have no idea. Reference was made to Carboni and Walter's paper, and I realized I'd never read it. And I talked to Eva plenty of times about her work, and I sort of hazily grasped some of it. And she was always talking about how wonderful this paper by Carboni and Walters was. So I finally got around to reading it, and I thought, well, heck, there's got to be some version for double categories, right? But as I was working on it, I started realizing that there were all these weird potential applications, and I actually presented on this work for the first time at ACT in 2021, I think, and I made all these sort of extravagant promises about what I thought I might be able to do with some of these ideas, and I finally got around to working out some of these notions over the summer. So bicategories of relations have been used in knowledge representation. So Evan Patterson wrote a paper back in 2017 using bicategories of relations for this notion of a relational O-log. So O-logs are these things called ontology logs, which are ways of representing, right, how concepts and attributes and facts about them relate to each other. And his observation was basically like, okay, look, we've got this nice notion of a functional O-log due to Kent and Spivak, but not every relationship that you might want to model is just functional. So we're going to look at relations. And he wrote a really nice paper using bicategories of relations to do precisely this. The issue, though, at least in my opinion, was that the functional O-logs are just finitely presented categories. They're easy in some sense. So bicategories of relations, right, sounds pretty high tech. There's a lot of stuff that goes into it. And one of the drawbacks that I saw as I was looking at it is that, like, if we're continuing to go with the conceit, right, that not just categories, but like higher categories are like somehow categorified, models of logic or whatever. If you just work with a bicategory, right, we should really be thinking of it as like a fragment of a double category where it's just giving you the pro arrows and cells, but it doesn't have any ordinary arrows. So if you were to think of this as like a logic over a type theory, it's giving you propositions and deductions. You have types, but there are no terms. There are no ordinary arrows. There are no individuals. So this is what double categories fix. In particular, with just a bicategory, equational reasoning is basically impossible. If you have a bicategory relations, you have the maps, but you got to impose equations to get the terms. So let's just axiomatize it and just work with a double category. So I'm thinking of these as sort of supplying the missing type theory for the bicategorical viewpoint in knowledge representation. This makes equational reasoning way easier. It makes computer implementation easier. And ultimately, I want to use it for data migration. Some of that's on the agenda. Some of it is worked out. This is the paper on double categories of relations. Oh, no, sorry, that's not the paper. That's a blog post on using Cartesian double categories for knowledge representation. And there are also some slides there as well. So that is, I think it's 50 minutes exactly. So thanks a lot. It's been a great conference. I'm happy to answer any questions.
Okay, thank you for your talk. And yeah, if there's any questions, feel free to jump in and ask them. Oh, we already have a raised hand. Go ahead.
Yes, please go ahead.
Thanks a lot for the very beautiful talk. I just have a question on the very last slide. I'm not sure I get what you mean by that they don't quite have a type theory, so equational reasoning about term is hard but not impossible. So this is really my opposite view on Cartesian bicategory. So I'm it's kind of confusing to me. I mean, they also Carbone and Walter say that they can basically do regular logic and regular theories. So it's to me Cartesian bicategory are really much about logic.
Yeah.
Regular. It's really kind of the basic stuff on regular logic. So I'm not sure I understand maybe what you mean about the terms. It's maybe I'm wrong there. I don't understand.
Well, so I'm thinking. So I'm mostly kind of approaching this right already from the viewpoint of working with an equipment. So the source target map is a fibration, right? And generally, well, actually it's a bifibration. And I'm thinking in terms of like the fibrational semantics of logics over type theories. And so what this is, what the fibration gives you, right, is that in the total space, in the domain, right, of the fibration, that's sort of acting as the logic part, being the propositions and the deductions. And then those project, well, which are in context, right? And those project down to the base of the fibration, which contains the types and the terms as the tracking that on to double categories, right? The total space, the domain of the fibration is the pro arrows and the cells. So those are acting as the propositions and the deductions. And the ordinary arrows are the terms. So those project into the base, which has the objects and the ordinary arrows. So the objects are the types and the ordinary arrows are the terms. So if you think of a bicategory as a double category that sort of like is missing ordinary arrows in some sense, you're precisely missing the terms.
Okay. Thanks a lot.
Sure. Yeah, no problem.
I think I kind of understand your perspective is
Okay.
more type theory than mine. I was thinking in terms of categorical logic. So you have this correspondence with the existential hyperdoctrine for Bertrand Becker. Okay.
Yep.
Thank you very much.
Let's see, there's a question here in the chat. Are these sub-object comprehension schemes related to the pre-sheaf objects Roald presented the other day? I don't know. And that's something I want to talk to Roald about because I haven't thought about it. I do think that there's a fair amount of overlap. I sort of mentioned, right, that I'm actually, I've sort of assumed myself to have this like pseudo inverse, right, to actually sort of ignore the admissibility issues that Roald is precisely trying to deal with. So I don't know if like I'm just like skirting his whole project or not, but that's something that I would really like to work out. So I don't know, maybe he's here and he can he is here. So Roald, if you're still listening, I would like to, you know, eventually sort that out with you. Sorry, I don't have any more on that right now. Oh, yep. Okay, there he is. Okay.
Are there any other questions for Michael? I guess a question that I had was, we have this characterization of the double category of spans for span E for E with no finitely complete or whatever. New produces characterization of rel E for E, a regular category. I'm wondering if it's also possible to characterize poly E for E, a locally Cartesian closed, locally Cartesian closed category. Is that like a future project that you could embark on?
I hadn't even thought of it, but yeah, that's certainly something.
I mean, it feels like it's in a similar flavor to.
Certainly could be, yeah. Yeah, I don't know. It's on the radar now, I guess. Yeah.
Okay.
That's a great suggestion. Thanks.
Yeah, that's okay. Okay, well, if there's no further questions, let's thank our speaker again.